Start soon, okay. All right, let's start. Do you have any questions? All right, so first of all, second midterm, right, is next Thursday. So the materials will be chapter 2 to 3.5, okay? And 3.5 has two portions. I will not put the sketching of solutions for repeated eigenvalues. In 3.5. Okay, so everything like chapter 2 to 3.5, not including the sketching part. So what else do I want to say? But you know, like, so sketching is still required, all right, and may show up for, you know, distinct or complex eigenvalues, okay? For that matter, first order PD solution may show up. Sorry, not PD, right? First order ODE may show up simply because you may have to solve for one single equation. Okay, and finally, not finally, some other things, right? So calculators still, right, allowed, that kind of thing, except that I am aware that you know, the TIs can solve for eigenvalues for you, and I think eigenvectors too or something. So all eigenvalues, eigenvector have to show work, okay? So you're not meant to use your calculator to solve for eigenvalues, eigenvectors. Yeah, I think it's similar. You can contact her to see when she'll hold the session. Okay, I think she will. I'll send her an email. What else? So one page of note, one-sided, same thing it was before, right? Same as before. One-sided, A4, that kind of thing. But you know, so this time I'll ask you to do this, submit with exam. So then I can see what your notes are. Yes, it's allowed. It's allowed, but like I said, right, it's allowed for calculation of numerical solution. Okay. So you're not you have to show work. Okay. Submit it. All right, submit it. So that's easier than showing on the camera. I think some people forget. So just submit it. It's better. Okay. Yeah, proctoring system is the next one. Respondus. Okay, is your new friend. Yep, take a picture. Responders, right, will be used in place of proctor track. Okay. So the quiz of this week, we'll use it. Okay, quiz this week for trial run. So we'll see what it is. All right, we'll see what it is. And if you have any issue with it, make sure you let me know before the exam starts. All right. As far as I know, it's required for the exam. So we'll do that. All right. So that's the gist of it. Okay. Questions? All right. So cool. So now today, right, the goal is to complete the 3.5. In terms of analytical solutions. Okay. And for that, I would like to revisit what we did last time and highlight my mistake again, right? So mistake from last time. So let's take one example, all right? The example is y prime equals to minus 2, 1, 0, minus 2y, okay? So we found that lambda equals to minus 2 are, so repeated eigenvalues, minus 2. The eigenvector, right, is 1, 0 as the only eigenvector. And so when we solve for the pseudo eigenvector, we got the one pseudo eigenvector is to be 1, 0. And so I wrote the solution, right, as, C1 times this plus C2 times this. Okay, this is wrong. Okay, and so the right solution, right, the right solution will be this. So it will be C2 times 0, 1. Oh, sorry, did I make a mistake? Oh, sorry, I missed a T, right? There's a T here. And then this is 1, 0, sorry, 1, 0. So 0, 1. Yeah, yep. Thank you, Carl. Yeah, I messed that up. Yep, 0, 1, right? And then there's a T here. Okay, there's a T here. So the right solution would be C2 times 0, 1 plus C1 times 1, 0 times e to minus 2t plus C2 times 1, 0 t e to minus 2t. Okay, this is the right one. And so I want to explain why. And so similar mistakes, right? For other examples. Okay, so I want to explain how, right? This is the right one and this is the wrong one. And then, put down the correct form for the solution. And then, repeat where we left off last time. So any question about, this before I explain why this is a mistake? So the mistake comes from this, okay? The reason for mistake, exactly, actually, I mentioned it last time, ironically, but I did not apply it to my solution. Reason for mistake is like this. A multiple of an eigenvector is an eigenvector, okay? But a multiple of a pseudo eigenvector is not an eigenvector. Okay. So for that reason, V2 is an eigenvector. So when we do this, all we're saying is we just multiply with an eigenvector. On the other hand, V1 is an eigenvector, is a pseudo eigenvector. Oh, sorry. Thank you, Ron. I mean, not a pseudo eigenvector. Thank you. Yeah, that's what I meant. Not a pseudo eigenvector. Yeah, and it should not be eigenvector to begin with anyway. Yeah, but what I meant is more of a point of a pseudo eigenvector. Yeah. So, all right. So V2 is an eigenvector. So when I plug this in this structure, is an eigenvector. But V1 is a pseudo eigenvector. All right. Multiply by it like this actually is absolutely wrong because that's not preserving the pseudo eigenvector structure. So preserving the pseudo eigenvector structure is this right here. That's the whole idea of this complicated expression. But it's not that hard. The reason is this, okay? And now we'll go back to the abstract form and show you. But let me explain it briefly and I'll do the abstract form again. Briefly, what happens is we should say that V1 is a pseudo eigenvector corresponding to V2, okay? V1 is a pseudo eigenvector corresponding to V2 in exactly this relationship. So therefore, in the solution, if we multiply, V2 by C2, then this solution also gets multiplied by C2 correspondingly. That explains the C2. What about the C1? The C1 is the degree of freedom, is a free degree of freedom for this solution right here. Because remember last time I remarked that this is not the only choice, right? This is not the only choice of solution. But basically 0, 1 plus any constant times the homogeneous solution will solve this system. So this is a C1. This is the freedom. This is a C1 right there. So in respect, right, what happens is like you solving it for C2 like this. And you conclude that the solution is C2, C1 like that. Okay. So this C2 is fixed because it's right-hand side. The C1 is free in respect to the system because it's multiplied with any homogeneous solution, right? 1, 0 is a homogeneous solution for this system. Okay. And so that explains this. So this whole thing captures the homogeneous, captures the pseudo eigenvector structure that we need to put in. All right. Any question here on the association with C2 and C1 in this respect? We'll do more examples. All right, we'll do more examples. Yeah, I'm finishing 3.5. Right, I'm finishing 3.5. Basically, repeated eigenvalues with non-full set of eigenvectors. I'm correcting the form of the solution that I put down last time, and we will, after the correction, after explaining, okay, the idea, we're gonna continue with the 3x3 examples that we did last time and just end on that note. It will take a while to just do all the examples. Okay. So let me repeat the reason again, all right? Because it will be helpful to see the structure. So the abstract structure of the solution, okay? So again, let's suppose that I have y prime equals to ay. Let's suppose a is 2 by 2. I consider, right, so case 1, I have lambda 1 and lambda 2. They're different, okay? Or even that. So, okay, let's do that. Lambda 1 not equal to lambda 2. So I have two vector, v1 and v2, okay? I consider solution of the form yt, right, equals to, okay, hold on, sorry. Let me do this. Suppose I don't know what the solution is, but I know lambda 1 is not equal to lambda 2. I consider my solution to be of this structure, v1 e to lambda 1t plus v2 e to lambda 2t, all right? Suppose I don't know, okay, I don't know what v1, v2 should be, okay? We know what they are, but pretend that we don't, okay? And now, so the mistake I made last time was to impose a C1 and C2 in front, which is like what we're used to for solution, okay? What I want to do now is not having the C1, C2, and that's the right way to think about it. Because here, I just want to look at V1 and V2 as some generic vectors. And so, right, what happens is I will plug in, okay, and discover to see what this is. If I plug in, then I got my y prime will be lambda 1 v1 e to lambda 1t plus lambda 2 v2 e to lambda 2t. Okay, and it's supposed to be equal to ay. So that's going to be a, right, times, right, a times this whole thing. So let's do this, right, ay, which is a v1 e to lambda 1t plus a v2 e to lambda 2t. So if you do this, then you discover, right, that matching terms, that lambda 1 v1 must be a v1. Lambda 2 a v2 must be lambda 2 v2. So you discover that for this to be true, so in other words, these guys are eigenpairs. Okay. But so notice then that this is my solution. And so what I say is, right, what I conclude is this, that V2 will be eigenvectors. V2 will be eigenvectors, whatever they are. V2 will be eigenvectors, whatever they are. So therefore, right, when I solve for my example, let's say this, right? Let's suppose that you have y prime equals to 1, 2, 0, 1, okay, y, right? So your lambda equals to 1 and 2. If you look at lambda equals to 1, your V1 will be, right, if lambda equals to 1, then you got 0, 0, 1, 1. So your V1 will be 1 minus 1. If lambda equals to 2, then you got minus 1, 0, right? 1, 0. So your V2 will be 0, 1. Okay. So notice, right, when we say this, it's actually not quite correct, right? If we want, we should say this. Because, you know, I mean, I know, right? Doesn't matter what we write, eventually we'll write the solution correctly. But if you want, this is the correct way to write the eigenvector, because anything would be an eigenvector in this case. Anything like this would be an eigenvector in this case, as long as these are not zeros. So therefore, right, matching exactly, you see this structure. So the C1 is implied when we call it an eigenvector. That's what I'm trying to say. It's not solving like this and put it down at the end. But we do it anyway, right? It doesn't matter which one where we do it. But I want to say that because of the subtlety of the pseudo eigenvector, it's better if we emphasize it up here rather than down there. So it's going to be C1, right? 1 minus 1. Or rather, right, let me emphasize the structure again. Is V1, right, e to lambda 1t plus V2 e to lambda 2t, which then exactly falls into our previous form. Is that okay? Like that. So now, if you look at the one we looked at before, right, that y prime equals to, okay, sorry, case 2, right? Case 2, when you only have, when you have repeated eigenvalues and, right, only one vector, okay, as eigenvector. Or let's just say 1v, okay, as eigenvector. So the abstract structure, right, is that when we look at y prime equals to ay, you let solution y to be v1 e to lambda t plus v2 t e to lambda t, like that. No c1, c2 in front. That's what messed me up last time. I put c1, c2 up here, and then I get confused, right? The c1 should not be up front like this, because when I put it like this, I imply that the whole thing somehow preserves its structure. But if it's a pseudo eigenvector, this is not true. So I just keep v1, v2 separately like this, all right? And then the nature of the vector is kept inside. Okay, then I plug in. Okay, I plug in. So I got y prime is equal to lambda v1 e to lambda t plus v2. Okay, I got e to lambda t plus lambda t e to lambda t. Okay, I will group term first of all. All right, I'll group term. I will combine e to lambda t together to give me lambda v1 plus v2 e to lambda t plus v2 lambda t e to lambda t. Okay. On the other hand, it's supposed to be equal to a times y. So it's supposed to be equal to, right, a times this, which is a v1 e to lambda t plus a v2 t e to lambda t. And so here we see what happens. Then a v2 must be matched with v2, lambda v2, and a v1 must be matched with this. So in other words, right, we got a v1 must be lambda v1 plus v2, and a v2 must be lambda v2, or, right, as we say, a minus lambda I v1 must be v2, a v2 is equal to lambda v2. Or if you want, right, actually you can impose this. A minus lambda I v2 is equal to 0. Okay. So example, right, is exactly what we just said. Y prime is equal to minus 2, 0, 1 minus 2y, right? And hold on, give me a moment. I think that's that, right? Oh, sorry, 1 up here. Okay. And so lambda, right, is equal to -2 -2. If lambda equals to -2, then you got 0, 1, 0, 0, right? So that's A minus lambda I. So first you see we trace this. What example are you referring to, Ron? This current one? This equation? This equation right here? Why do I not get V2 equal to 0 if AV1 is equal to lambda V1? So that actually, if you think about it, that actually will imply that V1, V2 are two eigenvectors. So that exactly goes against our assumption. So that's not the case we're discussing, right? Exactly, that will be this case right here. That's what you're referring to, right? So exactly the reason is, right, and the reason is we are in a case where we only have one V as eigenvector, okay? That's the thing. If you have two eigenvectors, then that's what you're saying. Now, both can happen, and that's where, right, this thing can be confusing. Both can happen. I cannot tell you what rule, right, it is that when you have one or the other. But when you realize what case you're in, then, you know, the system that you solve for will be different, okay? So here, right, exactly, first you try out. So here, right, let me say this. If you have two solutions for V2, you're done. You don't need to solve for the pseudo eigenvector. So no need for pseudo eigenvector. But exactly, you see, right, here you only have one solution, which is and let me be careful here, right? I'll do this, C2, 1, 0. So you see the difference is now I include the C2 into my choice of V2. I will not put the constant down there. I put the constant right here. Is that okay? So that's my V2, but only one. Now, right, so that's the second part of the system. After I solve for V2, I will plug this into here, okay? So A minus lambda IV1 will be 0, 1, 0, 0 times V1 equals V2. Okay. So what solution do I have, right? So if this C2 bothers you, right, just ignore it for now. Because just solve for one solution like we did before, which is what was it, right? 0, 1, right? Zero, 1, right? But you see, if it's 0, 1 solving this without C2, then all you need is a C2 right in front to solve for the C2. But this part right here is just a particular solution, right? One particular solution. Right? This equation has one degree of freedom. So you need that degree of freedom. That degree of freedom is C1. Yeah, thank you, Sada. Thank you. Yes, thank you, Sada. Yeah, V1. I meant V1. Yeah. Okay. Plus C1, right, times the homogeneous solution, which is 1, 0. Okay. So this is the homogeneous part. Are we okay? So now, right, then I will match it exactly with the structure of my solution. So y is supposed to be, right, v1 e to lambda t plus v2 t e to lambda t, which is c2 0 1 plus c1 1 0 e to the minus 2t plus c2 1 0 t e to minus 2t. Any question? So, right, the text, if you will, give you this kind of solution. They write e to minus 2t x0 y0 plus t e to minus 2t y0 0. This is on page 319, but you can see that it's exactly like this. So, okay, Carl, right? This requires you to recalibrate your understanding of the constant a little bit, okay? Like the mistake I made last time, was just to go with the structure C1 vector E, C2 vector E, okay? That's a wrong structure to think about because, like I said, right, the idea is a multiple of an eigenvector is an eigenvector, but a multiple of a pseudo eigenvector is not a pseudo eigenvector. So we need to drop that idea. It's fine for the explicit eigenvector, distinct eigenvalues or complex eigenvalues case. That's fine. You can think of it like that. Doesn't matter. But here you must be a little bit more precise. And to be more precise is what, right? To be more precise is to embed the constant when you solve for things. For example, if you look at this system, do you agree that V2 is not just this without a C2, right? When you solve for this, V2 is any constant times this vector, right? To solve for this. Agree? Now then you lift this whole structure to bring it down to the V1 because the solution says this times V1 is equal to V2. So you lift this whole structure down here and solve for, this is exactly, right? This is A minus lambda I V1 equals to V2 here. The difference between this and last time is I lift the whole thing, meaning I carry the C2 down too. Why? Because I insist that V2 is this whole structure. It's not just this. It's not just this. All right. So then how do you solve this structure? So here, right, you must think that C2 is fixed in this second equation. It's a fixed element. It came from the top equation. Okay. Then the approach is the same. You find one particular solution. What is a particular solution here? I claim that the particular solution is this guy right here. Yeah, and then hold on, let me explain to Carl, right? This is one particular solution, but the particular solution does not include all pseudo eigenvector, right? The pseudo eigenvector would require the homogeneous part, right? It's the same idea as, right? This alone does not count for every eigenvector. Multiplied by C2 account for all eigenvector. So same thing here. This alone does not account for all pseudo eigenvector, right? This and this together accounts for all pseudo eigenvector. Is that okay, Carl? For me, that's the easiest way to remember this. I can tell you some other kind of tricks, but for me, that's not conceptually, comprehensive, right? However, you want to memorize this structure, right? Some people like to combine like the C2 together like this. and then leave the C1 outside. Yeah, of course, because those are the freedom for you to fit the initial condition. So the book approach it from the initial condition point of view, right? I approach it from the freedom constant point of view, but both of our points of view are the same, equivalent, right? But I want to tell you that to get over your confusion, right? Do try to remember that when you solve for this, there is some freedom involved already, okay? We just choose to embed that freedom when we write down the solution. But for this case, I insist that we write the freedom, we capture the freedom as we solve for the vector. That's what I'm saying. Okay, does that make sense? Yeah, all right, we will do more examples, all right, as you see, I'll repeat it. So Albors, yeah, so exactly, right? Here is where like the idea of one eigenvector and one vector and many vectors can get a little confusing. But so that's why I say, right, I refuse to put the C1 and C2 in here, right? Because I want to capture V1 and V2 in terms of its class. And that's actually what this is here, right? When you write down this solution, you never say what V1 and V2 must be. So all you say is V2 is anything that's solved for this. So V2 is any eigenvector. That explains why you put the C2 down at the end. But like I said, right, same idea for V1, right? V1 is any pseudo eigenvector. So exactly like you said, right, this spans the whole pseudo eigenvector structure, and that's why I use it. Whether you want to count it as one class, right? I would rather count it as one class of pseudo eigenvector, but one space. Yeah, absolutely. C1 could be 0 depending on your initial condition, right? That's where your initial condition decided. But when you want to write down the general structure, you cannot miss the C1, right? Whether it's 0 or not is decided by your initial condition. I'm not here to decide that. I'm here to give the most general structure of the solution. Then I must include the C1. Yeah, this is a pseudo eigenvector, Sagar. This is a pseudo eigenvector. Or this is the space of the pseudo eigenvector, if you will. It's a space of the pseudo eigenvector. The vector space of pseudo eigenvector. All right. Any question? What do you mean by two solutions? This is the particular solution. I'm not sure I follow your question. You can ask me after class, all right? I'm not sure I follow your question. All right, so let's carry this to, so for the rest of the class, right, I'm just gonna do more examples and then go with the repeated 3 times case. So we look at, the next one we look at was textbook problem number 2, where we look at this case, okay? And so just repeating what we did last time, when you look at determinant of A minus lambda I, you got 2 minus lambda, 4 minus lambda plus 1, which is lambda squared minus 6 lambda plus 9. And so you got lambda equals to 3. So if you look at A minus lambda I, you got minus 1, 1, minus 1, 1. So you only get one eigenvector. And so here, right, I insist I call this C2 times 1, 1. Or you will, right? The solution, if you will, the solution is this times V2 is equal to 0. Then you easily see that V2 must be this. Okay? So in this case, I keep the C2 here. Then, right, to solve for V1, I look at, so to solve for V1, okay, I look at this times V1 to be C2 times 1, 1. All right. What is V2 then? What is V1 then? So V1, right, will be a particular solution. What is a particular solution here? If you hide the C2, right, then you see that 0 and 1 here would work. Yeah. So, but here, right, our board, after you got that 0, 1, you must include with C2. Yeah, because the C2 is included here. -2 and 1, -2 minus 1 also works. So if you want Sagar, you can do this. But then both of you, right, Albor or Sagar, you must then add C1 times 1, 1. Okay. And I hope you see that both of your classes are the same. These are the same vector space. Is that clear? Because, right, actually, if you choose 1 here and -1 here, you will get to -2 minus 1. Oh, wait, hold on. 1 here and -2 here, right? Yeah. Is it okay? So either this would fit for V2, for V1. And so your final solution would be, pick your favorite. I'll go with, I think, Saga's version. So I'll go with C2 -2 minus 1 plus C1 1, 1 e to 3t plus C2 1, 1 t e to 3t. So this fixes, right, my mistake last time for this example. Any question on this? Is it okay? Then next, right, look at, now we move to a 3 by 3, where we look at y prime equals to ay, a to be 2, 0, 0, 2, 1, 0, 1, 1, 1. So eigenvalues are 2, 1, and 1. When lambda equals to 2, right, I look at 0, 0, 0, 2 minus 1, 0, 1, 1 minus 1. And so my V1, right, normally I would write 1, 2, 3, right? And here actually doesn't hurt because it's not involved with the business of 1, 1. But let's just, out of principle, do this. Okay, and you agree. Because, right, the whole thing is that, right, the whole thing is that, right, it should be that this guy times V1 is equal to 0. So V1 is this. Okay. Now, if I look at, right, lambda equals to 1, then I got 1, 0, 0, right? 2, 0, 0, 1, 1, 0, right? Times. So I'll cheat here a little bit, okay? Well, it doesn't matter. I think let's not, right? Let's not be too artificial. Let's do V2, okay? Equal to 0. So the question is, how many V2s do I find here? How many V2s do I find here? 1 or 2? 1, right? So my V2 will be, the first coordinate must be 0, right? And the second coordinate is also 0, and the last coordinate is 3. So let's say 1, and then times C2. Is that okay? But because I only have 1 here, I will need a pseudo V3. Is it okay here? That's the natural flow of the information as far as I can tell. That when you solve the solution, this is how you can naturally think. Okay. Now then, what is a pseudo V3? So let me say this, right? Pseudo V3, to be explicit, corresponding to V2. Yes, that's what it is. In other words, right, I need 1, 0, 0, 2, 0, 0, 1, 1, 0 times V3 is equal to C2, 0, 0, 1. So what's V3? V3 will be a particular solution, right, plus a freedom degree, a freedom part. The free part is C3 times 0, 0, 1. Are we okay with this? Now, what is a particular solution then? Should be 0, 1, 0, right, Ron, with a C2 in front. Correct. Okay. So now put things together, right? What is my final solution? So let me do this, right? So it will be V1, right, e to the lambda 1t plus V2. Now, so the question is, the V2 here, is it t e to lambda 2t, or is it e to lambda 2t in the way we put it? Which one? Yeah, Lauren, right? The reason is the C2 here is attached to the right-hand side. Okay, if you put a C3 here, and ignore this for now, right? Do you see that this cannot match with this? Because simply C3 and it's not C2. Right, so the C2 is because this is a particular solution matching with this. And it's C3 because this is just the freedom of this guy. This is the homogeneous solution. So it's the free part. Right, this is particular of V2. Got it? Yeah, that's how you're not confused. You see which part must solve for what. Okay, and which part is free. So back to my question, right? Which one is which? Does the V2 get the T or does the V3 get the T? Yeah, okay, Lauren. That's exactly the thing, right? So why is C2 used here? C2 is used here as the freedom part of this equation. Do you see it? Because any C2 here would solve this. And then, right, I'll answer you, Daniel. Then you lift the C2 down here. Okay, why? Because I need A minus lambda I V3 to be V2. Okay, Lauren. So that's why I need to lift the whole C2 structure down here. Then you just contemplate what solves this. Now, you see that C2, right, must be, so basically if without this, right, then the solution is 0, 1, 0, as you know, Ron and someone else said. But then because it has a C2 in front, I must match it with a C2. Is that okay with you, Lauren? So the C2 appears twice exactly because I lift the whole C2 structure down here. So this C2 must appear here too, right? Same as like without a C2, I only get 0, 1, 0. All right. So twice because it's itself. All right, so let me see what Albor was asking. Oh, Daniel, right? Or if C3 is 0, then the remaining vectors are different. So V3 would not be equal. If this is 0, okay, all right. So still question or no? Did I address everyone? Did I miss anyone? So now to patch things together, right? It's just which guy get the T? Is it a V3 or V2? Which one get the T? V2 gets the T, yes, because the eigenvector gets the T. The pseudo gets the non-T, right? That's it. So here, right, V2 is the eigenvector, so it's this. So that's where I don't want to be so pedantic and, always put the T, at the end or something, right? Just the eigenvector get a T. So right now, putting things together, right, my V1 is this. And this is my lambda 1, right, if you want. So C1, 1, 2, 3, e to the 2t. My V2, C2, 0, 0, 1, t e to the t. And my V3, the eigenvector gets the t. The eigenvector gets the t. Well, to make you confused even more, there's a t square coming up. Okay, but the eigenvector gets the t coming from exactly right here. Okay, and when I look at it, this. Okay. Any question? All right, so now moving on to the case when we have, yeah, Lauren, of course, but it is an eigenvector that is very unrelated to this business, because when we mean that, we are looking at the repeating case, right? You know what I mean? The repeating case. So okay, I think this statement needs to be clarified, right? For the repeating eigenvectors. Yeah. So here, right, the business is only between V2 and V3, right? V1 is by itself. It plays its own game. It's fun. You know what I'm trying to say? Yeah. So this statement refers to the two that's repeating. It has nothing to do with the other one. Yeah. Okay. So the next one, right, is where we repeat 3 times. Okay. Example. So you know what the question is, so I will not even write y prime equals to ay. Is this, all right? So lambda equals to 1, 1, 1. Okay. And so let me do this, right? So lambda equals to 1. There's only one lambda. Then let's investigate the eigenvector structure first. So a minus lambda I, right? Let's call it v1, right? There should be at least one of them. Okay. What is this? 0, 0, 0, 2, 0, 0, 1, 1, 0. Okay. How many v1 do I have here? One, right? One v1. Namely 0, 0, 1. And let's not forget to put a c1 in front. Is this okay? All right, so we're missing 2, right? This is very severe. We're missing 2. So what do we do? So now, right, this is the new structure that I'm introducing. So the structure that we consider now is y of t is v1 e to lambda t plus v2 e to lambda t. Sorry, right? Okay. For some reason, right, you see that this v will flip side. So I'll revisit, okay? So I'll revisit this to change the notation to v3. You see. Yes, yes, exactly. So that's why I'm considering this structure right now. T plus v3 t squared over 2 e to lambda t. Okay. So, but notice, right, there's a t squared over 2, and you see for obvious reason. I don't want the 2 hanging around. All right. So now plug in y prime is lambda v1 e to lambda t. v2, right, e to lambda t plus lambda t e to lambda t. v3, right, you see that's the division by 2 helps this. T e to lambda t plus lambda t squared over 2 e to lambda t. Is that okay? Now I will group terms. So what is the term with e to lambda t? v2 and lambda v1. What's the term with t e to lambda t? Lambda v2 plus v3. See how the structure just repeats itself? And clearly, right, v3 lambda v3 is the only one with the t squared term. Okay. That's taking care of differentiation. Now, obviously, this must be ay. So, right, take a, multiply with this whole thing. I will get a v1 e to lambda t, a v2 t e to lambda t, a v3 t squared over 2 e to lambda t. Matching terms, you see obviously what system must satisfy. Okay. In other words, we get a layer of 3, right? Where I start out with a v3 is lambda v3. Then a v2 is lambda v2 plus v3. And then AV1 is lambda V1 plus V2. Or let me put this in terms of a system. A minus lambda I, V3 is 0. A minus lambda V2, A minus lambda I, V2 is V3. A minus lambda I, V1 is V2. All right. So I will say this, right? V3 is an eigenvector, or rather the eigenvector, if you have only one, right? That's the case here, the eigenvector. I mean, or the eigenspace, okay? V1, V2 is the pseudo eigenvector let me put this, right, corresponding to V3. What do I mean by that? It solves the one with V3, okay? And then V1 is a pseudo vector corresponding to V2. All right. So this suggests that, right, exactly, that's why I say I should call this V3. Now, of course, if you're used to it, you know what you're doing, that doesn't matter, right? You call it V1 if you will. I don't know. Want to call it V1 or V3? I can call V1 and just start solving. You want to call it V3? So from previous problem, right? So maybe let's call it V1, okay? So I have V1 equal to C1 times 0, 0, 1. So this suggests, right, that starting with this, I need to plug it to right-hand side. So the next level will be A minus lambda I, V2 is equal to V1. Right? So A minus lambda I is 0, 0, 0, 2, 0, 0, 1, 1, 0. Yes. What's my V2? My V2 will be C1 times 0, 1, 0 plus C2 times 0, 0, 1. Is that okay? Zero, 1, 1. Yeah, but you see, your 0, 1, 1 would be this choice, where this is 1 and this is 1. You see, that's exactly why we need to include a second freedom. So my choice includes your choice. So yeah, it could be C1, 0, 1, 1 plus C2, 0, 0, 1. Is that okay, Will? So in fact, right, in general, if some of you are observing, it's going to be like this: 0, C1, C2, if you will. That's what it says. Whatever C1, C2 it is. Where V1, right, if you want, is 0, 0, C1. All right. So now what's next? A minus lambda I, V3 must be equal to V2. The last layer. So that would be 0, 0, 0, right? 2, 0, 0, 1, 1, 0. V3 is equal to 0, C1, C2. What would that be in terms of C1, C2? Yeah, the eigenvector is V1. Yep. I'm solving for the two pseudo eigenvectors. Are you saying for the particular solution here? We need C1, C2, all right, because C1, C2 is in here. We need C1, C2. What would C1, C2 be? By the way, right, so first of all, right, V3 will be a particular solution, right, particular plus homogeneous, right, as always. So particular solution is something involving C1, C2. Homogeneous is when you pick up the C3 with exactly the same thing, 0, 0, 1. Are you okay with that structure for now, right? We'll go back to guess to see what the C1, C2 must be. Guess what one of them. But this is a homogeneous structure. Same as the homogeneous structure here, right? But here it takes on the C2 because it comes from the V2. Is that okay? So this is the freedom of the V3. Any choice here in terms of C1, C2? So I think, right, if you call this X, Y, and Z, then you got 2x, right, is equal to C1, and 2x, sorry, x plus y is equal to C2. So you could choose C1 over 2, and then C2 minus, right, C1 over 2, and then 0. That exactly, you know, this C3 right here express exactly the freedom on the third part. So that's V3. All right, yeah, Lauren. So basically, right, you see that I'm lifting, right, the whole C1, 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 C2 structure from above, right down here for the V3. Now you just have to find a solution for V3 that satisfies this. Now I guess here, I don't know, eyeballing seems a little bit tough. So you just call it X, Y, and Z and see what X, Y, and Z have to satisfy, right? So if you plug in, you see the first equation says nothing because it's 0 equal to 0. The second equation says 2x has to be equal to C1. The third equation says x plus y has to be equal to C2. And so then x must be C1 over 2. Y must be C2 minus C1 over 2, right? And technically speaking, right, if you look at it like that, you can say, well, then your C3 is right here, if you will, right? Or because I only have the C3 cover, I put a 0 there. All right. So what's my solution then in this way? So actually it's the reverse, right? I start out with the eigenvector. So it's v1 t squared over 2 e to the lambda t. Then I start out with the pseudo corresponding to it. So this would be, yeah, still t, right? And then I start out with, then I finish with the one that corresponds to the v2. So I kind of go backward. Is that okay? So it's going to be the whole caboodle of C1 over 2, C2 minus C1 over 2, 0, plus C3, 0, 0, 1, right? T squared over 2, e to lambda t, plus 0, C1, C2, t e to lambda t, plus 0, 0, C3, e to lambda t. What was V3, Saga? Oh, thank you. What the heck did I do? That was a mess. Sorry. Thank you. Yep, I did it wrong. So how do I fix? I'll fix it here. Thank you. E to lambda t. T squared over 2. Yeah. No. I I switched it and I switched on myself. Yeah. This is correct, right? This is correct. Is it okay? So this is as complex as it can get. All right, I promise you. Any question? Oh, because I didn't pay attention. It's 111, right? Yeah. Yeah. All right. One last example. Okay. So here, right, lambda equals to 111 again. So when lambda equals to 1, right, let's look at a minus lambda I times v is equal to 0. So what do I get? 0, 0, 0, 2, 0, 0, 1, 0, 0. How many solutions do I have here? Correct, right? So in fact, you see that V here would be, let me do this, right? 0, C1, C2. Is it okay? So how many pseudo eigenvector do I need in this case? Right. I need one pseudo eigenvector corresponding to V. Okay. I need one pseudo eigenvector corresponding to V. So if I look at, right, 0, 0, 0, 2, 0, 0, 1, 0, 0, right? And let me call this V3, if you will, because this covers, right, V1, V2, right? Times V3 is equal to 0, C1, C2, for example. Let's see. Is there any solution here? Is there any solution here? No, right? No solution, but do you see why, and do you see how to fix it? The reason is this, right? There are two eigenvectors here. Yeah, that's the reason, but how to fix it? There are two eigenvectors here, right? Take only one eigenvector, exactly. We're bunching two eigenvectors into here, right? So exactly. So you only need to solve for one. Pick one, whichever one, okay? Pick one eigenvector. Whichever. So exactly, right? So the thing is, here I should really, right, not be lazy and write V1 is C1, 0, 1, 0, and then V2 is 0, 0, 1. And pick whichever one. So let's say, let me pick V1. So I'll get 0, 0, 0, 2, 0, 0, 1, 0, 0, right? Times V3 is equal to C1, 0, 1, 0. Okay. So what should my V3 be? Wait, does that work? Yeah, no. What's going on here? No, it doesn't work. That's interesting. No, that doesn't work either. So that's wrong. That's wrong. Okay, that's wrong. Yep. Hold on, right? Let me see. So I think I know how to fix this, but I need to have more time to present to you. All right. So let me say this. Let me let me not include this. All right, in whatever the exam and things like that. In the so for the exam, all right, do not worry about it. So exam for the repeated case, I'll only do this. Either a 2 by 2 repeating or 3 by 3, right? Where you have one, when you have lambda 1 and then lambda 2 and lambda 2. So you won't have the 3 repeating case that I just covered. That 3 repeating case is for your interest only. All right. So you must know this. All right. The quiz is just calculating eigenvalues, Sagar, not about solving. So the 3 repeating case, right? I hope you see has 2 choices. Either you have only one eigenvector, which we show. So no, right? The case of 2 eigenvectors is what we're looking right now. To be shown next lecture. Okay. So the 3 repeating case has 2 variation, 1 eigenvector or 2 eigenvectors. The 2 eigenvectors, I think, is some clever combination of these 2. I have to look at the abstract structure and show you again. Question. All right. So see you next Tuesday. See you next week. And the quiz this week will start using responders. Okay. And if you have any problem, let me know. Yeah. Thank you. You too. I'm not sure what review you're asking for, Mohammed. Your TA will run a review session for you, whatever she wants to run. The topics that I listed are like, from chapter 2 to chapter 3. Yeah. So your TA will run for you. Yeah. Mm-hmm. I'll send her an email to remind her, and she'll send our information for you. Yeah. I'm not sure I understand your question, Sagar. What eigenvectors are we looking at? Okay, Carl. So you cannot open the I haven't used responders. So what does it do? You can open the quiz, but you cannot open the submission page. Is that what's happening? How does it work? I haven't used it. Right, but when you click on the quiz, right, then the submission requires you to open a new tab because submission is right there, right? Or you need to open a new tab to submit.